Okay.
All right, so welcome back to the Neron Model Seminar. Our speaker today will be Boss Edixhoven, talking about the Hilbert functor.
Yeah. Okay. And I have 2 times 45 minutes, right? Okay. So, Hilbert functor and representability, that's what it is about. And I have 2 references for this that I use. One is the book FGA Explained, I think. And the other one is Bosch-Lütke Bomer-Renault. They also have a short description of this. And I looked at both, and in the end I decided to use more the statements from Bosch-Lütke Bomer-Renault because they did not make any Leferian assumptions. So the statements are more general than what you find in Nitsure's chapter 5 of FGA Explained. But if you want many details, I think still that is the best reference, FGA Explained, I think, right? And this is chapter 5 by Mr. Nitin Nitsure. And okay, good. So I think it is good to start with a bit of motivation. Why do we have to do this? And well, that is because of the other talks in the seminar. We want to do the Picard scheme, so this is needed for the representability of the Picard functor then. If you have a variety over a field, and say a smooth projective variety, like a curve, there is a Picard functor of that roughly takes its set of isomorphism classes of line bundles, but then over base changes. And to make it, how do you make line bundles, right? That is only one known way, and that is to make divisors. And divisors are closed subschemes of the scheme that you start with, of codimension 1, that satisfies certain properties. And so you want to have a scheme that parameterizes all these divisors, and that is the Hilbert scheme. That is one of the things that it can be used for. So if you want to know why Picard functors are representable in the not easiest cases, then you want to have the Hilbert scheme. Okay, and it is also useful. And also useful for other things, right? Also useful for other things. For example, each time you want to parameterize subschemes of some kind, you want to use the Hilbert scheme. Okay, good. So, and I said already, I follow Bosch-Lütke Bomer-Renault, so we can immediately go to paragraph 1, and I'll give you the definition. And then shortly after that, I hope to give you some examples. Okay, so here is the definition of the Hilbert functor. So for S, any scheme, we make it an X to S, any S scheme. This is a bit ridiculous. But okay, you can still define the functor. Let Hilb of X over S be the functor from the category of schemes over S to sets. It is the contravariant functor, and then we can write what it does. Actually, these notes that I have, I will scan them after the lecture and put them on my webpage, and then you can make a link to it. So I think you shouldn't take notes. You should just pay a lot of attention and ask a lot of questions. So if it is a scheme, a functor on this category, then it should do something with an S scheme T, right? And where do you send it to? Well, to the set of closed subschemes Z of X pulled back to T, right? So here is a bit of sketch. X lives over S. If I have T to S, then the base change will be denoted XT, like this. So we want closed subschemes of this, with, and now I have to pay for my ridiculous generality, but I did not invent this. This comes from Bosch, Edixhoven, and Neron. So you want this, at least this Z should be nice over T. This should be finitely presented, proper and flat. And especially the flatness is important. If you take, for example, for X, a projective space over S, for S you could take spec of Z or spec of a field, and then you could take a projective space over that, then I think these kind of things are automatic, but this is not automatic. That is important, the flatness. Okay, and of course, to have a functor, you should also say what you do with morphisms. So if I have T and T prime mapping to T, then you see that it's contravariant, because it should go from this set Z. Where does it go? It goes from this functor evaluated on T to that functor evaluated on T prime, and so you just pull back ZT as a closed subscheme of X pull back to T now, right? And you can pull back, well, that is also true, right? I mean, T prime goes to this, and then I have X T prime, and this is also the pullback here, so I think that explains it, okay? Is there any no complaints?
Some primes then there, right? Z of T prime, no?
Well, the Z goes to Z T prime, yeah.
And
And here also, yeah. Sorry, good, yeah. Yeah, okay, and in my notes, that is also true, yeah. Okay, so, well, I think, was it in the title that it said that I would do Hilbert and quote? Or was it Hilbert already?
Just Hilbert, but I mean.
Yeah, but okay, you could, before we do, I mean, like so many times, when you have a kind of talk about what Grothendieck did, you start by generalizing. And only at the end, the generalized things get proved, and then this is also representable. So we can also do a more general variant. Here is another definition. So the same situation, but now we're not going to look at closed subschemes. We are going to look plus F, an OX module.
Sorry, boss, if I can interrupt.
Yes.
Where's the map from Z to ZT prime coming from?
No, it is not. This is not a map. This is an object, an element of a set that is mapped to an element of another set. It is a maps to, and not a map. The map will go in the other direction, of course, right? Yeah. Okay. But we take an OX module that is locally fine. Oh yeah. Yeah. Okay. Finitely presented. Okay, point, then let quad, and this is depends on F over X over S, be the contravariant functor. So it goes schemes over S, two sets again, that sends T to S. And now I take the set of quotients, so Q is a surjective map from this F pulled back to T. Well, actually, here I should write again, I have X over S, I have T here, here lives this F, right? And then on XT, I have here a pullback, maybe if this is called P, then here I have Ft, and this is by definition the pullback of this F. And I want a quotient of that F, so that means a surjective map of sheaves of O modules on X pullback to T, say G here, the surjection of O xt modules with, and now again, like in the previous case, this Z had some good properties, now the quotient has to have some good properties. G locally finite presentation. O flat over OT. So the flatness means that this sheaf, you have this quotient Q to G, and well, if you take a point here and a point here over it, then you have a local ring here that is an algebra over a local ring here. You have a module, namely the stalk of this sheaf at that point, and it is also a module over the local ring here. And as such a module, it should be flat. Okay? If this is a spectrum of a field, then it is an empty condition. It is automatic. Flatness is true over a field. Okay? And it should have with its support, so the set of points where the stalk is not zero, the support should be proper over T. Okay? I think here the Z had to be proper. So why is that a generalization? That's a question for the audience. How do you make a map from this set into that set? Or actually you should first choose the F, right? And then, so for the F, you can take the structure sheaf, and you can say, in this situation, if Z is a closed subscheme of xt, then of course you have the O of xt, you have the ideal of Z, right? And somehow the structure sheaf of Z may be pushed forward to X as a quotient, right? And so in that sense, if the structure sheaf, if this sheaf F is the structure sheaf of X, then this quad functor is just the Hilbert functor. Yeah. Okay, so if we can prove representability of this, then we have it also for that.
Don't you want to factor out isomorphisms?
Ah, okay. Yeah, what is a quotient, right? So you can say here, indeed, this is modulo a kind of equivalence. And when are two things equivalent? Well, if I have, say, Q here and Q prime here, and this goes to G prime, and this is surjective, this is equivalent if you can make a commutative diagram with an isomorphism here, right? That is, two quotients are isomorphic if they have the same kernel. Right? You can also say that instead of parameterizing all the quotients, they could also say, well, I want subsheaves. So you could also say, yeah, or take the set of, but then I have to find another name, right? H in subsheaves of ft such that ft not H has the property, the required properties, right, of the G here. Yeah? Are you happy, Wessel?
I'm very happy.
Yeah? Okay, good.
Boss, sorry, you said that. So if we prove representability of quote, then we get that
Yeah.
for free?
Yeah, because then I say, okay, then we have in particular proved it when F is the structure sheaf of O of X. It's a structure sheaf of X, and then it is this one.
Sure.
Because submodules of a ring are just all the ideals, right? Yeah.
Yeah, so quad
And then also-
OXXS, quad OXS.
Yeah, okay, here is the magic
yeah.
formula.
Yeah.
Quad OX over X over S is the same as Hill X over S, right?
Sure. Yeah.
That is what Raymond says, yeah, and that's correct. Yeah, okay, so those are the things. Now let's do a few, what are the easiest examples? What is the simplest scheme? Well, there is of course, I think for S, we take the final object, right? So, two examples. And so what is the Hilbert scheme? And actually, without any theory, I can do the empty scheme over spec of Z. Okay? What do I have to do? I have to take a scheme over spec of Z, say T. I pull back the empty scheme. Well, that's the empty scheme. I have to parameterize this set here will be the subschemes of the empty scheme. There is exactly one. Okay, so then I know the answer, right? Because then this is the final object. If that is the functor that always gives me a 1-point set, that this is or in only one way isomorphic to spec of Z, right? As a fermitor, and that's it. Okay? So from, yeah, okay, good. Well, and I said 2 examples, right? So what is the other example you think? Hill spec Z over spec Z, right? Why not? What do I have to do? I have to take a scheme T. I have to pull back spec Z to T. That gives me T. So here, this, I will have to do this, right? T goes to T with the identity map. And I have to take closed subschemes of this. That maybe you have to, well, they have to be flat over this, but that's automatic. Closed, which no, they have to be flat over, I think I have to take open subschemes, right? So basically, when I have to take a closed subscheme here, well, I can choose for every point, basically, do I take it, do I not take it? So, yeah, but the flatness will tell you that it should be open. And but the complement also. Yeah. So what you're getting here, I can also tell you who represents this. It is the spectrum. It is spec Z, disjoint union spec Z, because the only way to fulfill the requirements is to take this T and decompose it, write it as a disjoint union of 2 open subsets. And that sometimes happens, and actually a map from a scheme to this exactly does that. Because, yeah, right, you can also write this as the spectrum of Zx modulo x squared minus x, if you like. And to give a map from a scheme to that means that you have to give an idempotent in the ring of global sections on your scheme, and that's the same as a decomposition into 2 disjoint opens. Yeah? So we have for 2 schemes, now we know the Hilbert scheme, and they give you a very wrong impression, actually. Because for many other schemes, well, let me do one more. And we can also do the Hilbert scheme directly of P1 over Z, I think. So what is let's think over the field. What are the closed subschemes of P1? You have the empty scheme, that is, say, divisors of effective divisors of degree 0. That's nothing. You have subschemes that are finite over the base, so they are effective divisors of some degree. And you have the whole P1. And that translates to that this is represented by the disjoint union for n in the natural numbers of n, because to parameterize effective divisors of degree n on P1, you need a homogeneous polynomial of degree n in 2 variables that has n plus 1 monomials, and you have to take them up to a common scalar. Right? So that is exactly this. And now I'm only missing the whole thing, but that you can only do in one way, so that means 1 spec Z for the whole thing. And this gives a better picture, because the Hilbert scheme, one of the theorems we're going to prove is that under nice conditions it's representable by a disjoint union of projective schemes, indexed somehow by numerical invariance of the subschemes that you parameterize. That's the, okay? Well, I can also do another one. And I'm not claiming that this is easy to see that it represents that fermitor, but it should be, if you take the points with values in the field, you should be able to see that it is correct, right? And maybe you can even see a morphism of fermitors from that fermitor to the scheme. And to prove that it's an isomorphism, that is a bit more work. But it's not strange. If I have, for example, x over s a smooth projective curve, or actually maybe just a smooth one, let's say a smooth projective curve, the Hilbert scheme, like the one we have here for the P1, also works here. The Hilbert of x over s is the disjoint union over n in n of the things that parameterize divisors. And to parameterize divisors of degree n on a curve, you have to take the symmetric product, right? It is x to the n. This is fiber product over s, modulo the action of the so this is x disjoint union x times s x modulo the action of s2 and so on. Disjoint union at the end with a copy of s for when you decide to take the whole curve. Oh, and if I want to have only that, say only this, I should say with geometrically connected fibers. Otherwise, there might be more subschemes of dimension 1. Yeah?
What is
Yes.
that SN?
Sn is a symmetric group.
Yeah, maybe it's a bit unfortunate notation.
Oh,
I mean,
oh, yeah, well.
No,
I-
it's
I-
the
I will-
power of S.
yeah, that is.
Sn is sim
Yeah.
of 1 to up to n.
Yeah.
Okay? And don't think.
Oh, I know it, but just to clarify.
Yeah, it's true.
For the
This
lack of-
S should be another font than that, maybe. Yeah. Okay. Good. Okay. That's fine. So, yeah, and I'm going to give you a theorem, but to state the theorem, I need one more definition. So, it's a bit technical, but I hope it will become less technical. A morphism of schemes, f from x to s, in the category of schemes, is strongly quasi-projective. Well, the quasi-projective. Well, it is again, I give two definitions for the price of one. You put the parentheses or you don't. If, so this is the thing I define, if it is a finite presentation, so you can write it down with finitely many data, and if there exists a locally free OS module E of constant finite rank. This is a bit, well, okay, such that X has a closed immersion and in the quasi-projective case you want a locally closed immersion or just an immersion, that is immersion into the projective space bundle that is given by this what people call a vector bundle, right? The P of E over S. Maybe people write PS of E, right? That is the. And what is this? If you like formulas with projes and sims, this is the proj over S of the sim, the symmetric algebra over OS of this E. Right? So if this E is just OS to the n plus 1, if it is this, then this is just the Pn over S, okay? And that is for people who do not, well, who have just to deal with projective schemes, sub-schemes of this, then it is fine to take that. Okay, you don't need to do this more general stuff, but people try to formulate these representability statements in highest generality, so I just copied it from Boschlik to Bowman-Renaud, like that.
So in
Okay.
particular, if S is locally no theory, this is just the same as projective, is that?
Well, no, nothing is local on the base, I think. Because, well, here also it says constant rank, but there are technical issues there, I think. Yeah, of course, if you have something like this E, then every point of S has a neighborhood on which this is really free. And then, so that Zariski locally on S, this projective space bundle is a trivial, can be trivialized, it can be this locally isomorphic to this. But I wouldn't vouch for the other direction. I mean, yeah? Okay, so given such an immersion, we also have a sheaf, let OX1. So that means we have an embedding in such a thing. And on such a projective space bundle, we always have an invertible module O of 1, right, that you have on the projective space. It is the, how to say, it corresponds to the divisor given by a hyperplane, right? It has n plus 1 rank space of global sections on Pn. It's the homogeneous polynomials of degree 1. Yeah, okay. We have this, and we pull it back to x. Right? So this is the induced very ample line bundle. And I think now that this thing has to be restarted. Yeah, 3 minutes left.
Just restart it, right? So
No, I think if there are 3 minutes left, yeah, you just have to push that red button twice. Okay, so can I now give the theorem? I think I can give the theorem in just 3 minutes. So this is by Grothendieck and Altman-Kleiman. So let f from x to s be strongly quasi-projective. Well, actually, why don't I just say strongly projective and let the quasi case in the notes, and that will save me some time. With its OX1, okay. Let f be a quotient of some, then we say f upper star of a b, calligraphic b, and then twist it with some power of this, right? So this number here is an integer, and it means that you tensor a pullback from a vector bundle from S. So this is a sheaf of O modules on X, and you tensor it with the new power of this, right? So you, yeah?
It's a bit hard to read the
Oh. Here is a nu, well, nu, Greek letter. With the B, an OS module that is locally free, finite constant rank, and the nu in Z. Okay, then this quad of f over x over s is represented by a disjoint union of strongly projective S schemes. Okay, and that's the statement. I think now we should stop the movie. 1 minute left.